In this video, we're talking more about alkenes to alcohols, and we've talked about this before using catalytic strong acids. So we're going to use H2SO4 in the presence of water. Now, the issue with this is that we do form carbocations, and we have to remember when we form carbocations that we could get rearrangements. So let's walk through this mechanism again. So we've got our sulfuric acid. We're going to protonate. We're going to form our carbocation at the most stable position here, the secondary carbocation. Now, remember that when you form a secondary carbocation, if you can form a tertiary carbocation, you can do a carbocation rearrangement. Really what's happening is we're going to do an alkyl shift. We're going to have this methyl move over to this carbon here. And what we have now is a much more stable carbocation. We have a tertiary carbocation. Now, the issue with this is that now when we have water attack, we have water attacking on a different carbon than we had expected because the alkene was on the end. Let's draw what happens here. So we've got water. We're going to have water attack at this carbon here. And then we're going to take another molecule of water, and we're going to deprotonate this because we don't isolate these high energy acidic compounds like this. All right. So now we have an alcohol that we formed, but we didn't form what maybe we were hoping for. We've got our alkene here. And so if you were wanting to make something where you had the alcohol here, would form a racemic product. This does not form. It's not the major. So let's write that out. It's not the major. So this is not the major product. Organic chemistry is not all 100%, so you'll probably get a little bit of it, but the majority of it's going to go through this carbocation rearrangement. Where we had a secondary going to a more stable tertiary, and we went through a 1,2 alkyl shift. Now, it was an alkyl shift because that was the only thing on that side that could move over to form the more stable carbocation. Notice again, our arrow is going from electrons, so we aren't never move the carbocation, so you never use arrows on those carbocations. So this doesn't form. We don't add our alcohol here to the secondary carbocation because we can form a more stable one. So in this video, we're going to be learning about a really cool way to go from an alkene to an alcohol without any rearrangement. We're going to be using this method called an oxymercuration method, and then we're going to get rid of the mercury by doing a reduction. So let me show you this reaction here. So we have mercury acetate, and you're probably thinking, isn't mercury like poisonous and very toxic? Yes, it is. However, you get the product you want. So the first step here is going to be a mercuration, and then our second step, we're going to reduce it using sodium borohydride, sodium BH4. And guess what? We get the alcohol that we couldn't get using just acid and water. We do get a racemic mixture. So notice on the previous slide, we couldn't get that alcohol drawn in green on the right. We had a carbocation rearrangement. So the nice thing with this method is that you do get Markovnikov addition. And we avoid rearrangements. we avoid any of those carbocation rearrangements. Let's walk through the mechanism together. So I'm going to start with my alkene. Okay, and then we're going to react this with this mercury acetate. And the cool thing about this mechanism, and what you'll see a lot in organic chemistry, is some of them look very, very similar. We're going to attack the mercury. We're going to kick out one of our leaving groups, which would be this acetate. Now, let's draw out what this acetate looks like. So OAC is equal to this. Think about acetic acid. So if you have a bottle of vinegar, white vinegar, I don't know, my mom makes really good potato salad and white vinegar is what we use in it. So white vinegar has acetic acid. So OAC is acetate. So it's an anion. I don't know why I'm talking about potato salad. I think I must be hungry. Okay, so we've kicked out our leaving group, and now this mercury is going to bite back. And this is going to form a three-membered ring, which is really similar to what we've seen for the Br2 addition to alkenes. So we have our tert-butyl group here. And now we have our mercury that was just added. We still have one acetate present, okay? And this mercury has a formal positive charge. This is really similar to that bromonium ion that we've seen before when we've had where this carbon that is more substituted is more partially positive. So these are very similar. The mechanism is really similar after this. So now we're going to take our water that is present in the reaction as a solvent, and it's going to attack. It's going to attack the most substituted carbon, and then we're going to kick out our mercury. Now it's still attached here on the end because it has that other carbon-mercury bond. Now we're going to have water that was added below, so it's added opposite here of our mercury. Now we kicked out an acetate, so we can draw that in, or you can use OAC, either is fine. And we're going to deprotonate this really acidic proton. And this is going to give us the first step. This is the product after the first step before we run our reduction. Now, the water that added is opposite of the mercury. Remember that that is blocking that top side. So this is coming from opposite. So this water attack is opposite. Let's make that in red. So that way we remember that this is an opposite, attacking opposite of the mercury. Remember that these groups, they're like blocking that side. And so any nucleophile that comes in is going to be attacking from below and at the most substituted. So it's opposite of mercury and attacks most substituted. All right, so here we have something that we do need to talk about, and this whole idea that it kind of looks like this SN2 reaction, right? We have water attacking, and then we have a leaving group leaving. And the thing that I want to talk about is water is not that great of a nucleophile. So let's look a little more in depth with this mercurium ion, and let's draw this out again. So we have this three-membered ring with this mercury, and it's a great leaving group. And one of the things that we need to think about is why water can attack, because water is a bad nucleophile. It's a poor nucleophile for SN2. Well, the reason here is that this is a really, really, really good leaving group. And there will be backside attack, similar to SN2, right? And I like to think about this mercury as it's kind of like this springboard. So when I take my water and I attack at the most substituted, this carbon-mercury bond just really wants to leave. It just pops it open. It's strained. It's also positively charged. It really wants to have those electrons. And so this is why water can be used as a nucleophile. There's a second thing I want to talk about is why. So it's also attacks most substituted. So why does it attack the most substituted carbon? And let's look at this. I'm going to redraw it over here. So actually, this carbon-mercury bond is actually a little longer on this side. And when we think about the partial positive charges, if I think about it being on this inner carbon, this would make a lot more sense than if I were to draw it on the other carbon. So let's redraw it and think about this partial positive charge being on the end. And we talked a little bit about this in our X2 addition or Br2 addition to alkenes, and that this carbon here, okay, this partial positive, it's more substituted, and so it can handle that partial positive charge more readily than if it were on the very end. This is kind of like a primary end, right? If I were to kick out that mercury, I'd get a primary carbocation. Here, it kind of looks like more like a secondary carbocation. And so this is why the most substituted carbon is attacked. Let's do a practice problem together. So here I've got a different alkene. We're going to use mercury acetate and water. Now, we know that the water and the mercury are going to be anti to each other, okay? So you could go ahead and just draw an intermediate that you know would form from this. So I'm going to take, I know, here's my alkene. I know I'm going to add the mercury acetate there and make that mercurium ion. So I'm going to push the methyl down, and I'm going to say, yo, the mercury is sitting on top. That's where we're going to think about this mercury being on this one. Now you could have it opposite. You could have the mercury going down and the methyl coming forward. And the key here is that when we add the water, we know that the mercury is going to be opposite of the water. So if we draw what we have from this reaction, the mercury will be on the less substituted side, and the water will be opposite, and it will be an OH group that was added, right? And then our methyl is now forward. Let's draw a partial mechanism here to show it. So we're going to attack the most substituted side, and we're going to kick up the mercury. That water is pushing that methyl forward. All right, so this is backside attack. Okay, and then there is a net anti-addition. The mercury and the OH group are anti to each other. So these are opposite or anti, however you like to remember that. These are opposite. The mercury and the OH group are opposite across that alkene. Another point to remember is that the mercury is on the least substituted side. And the OH goes on the most substituted side. All right. Let's talk about getting that mercury off. We just want the alcohol. Remember, we're going from alkene to alcohol. This is an intermediate that forms. Oh, and I should also note here that this is racemic. And it's racemic because we could also draw the mercury on the bottom here. And then the water is attacking, most substituted side, kicking this out. That would mean that the OH group is coming forward and the mercury is back. So both chiral centers here would be switched. So we do get a racemic product for this. Let's go over the next step of this reaction, which is this demurcuration. So we're going to draw our intermediate here that we have. We have our mercury that was added. Our methyl is here. I'm going to write Me just so we can keep track of everything. You don't have to. You could just keep it as a line. And now we're going to get rid of the mercury. So this demurcuration step is using sodium borohydride. Sodium borohydride is a reducing agent. And we would typically do this in water. So you would add sodium borohydride, and then you actually go through a radical type mechanism here. And what happens is that we get rid of the mercury, which is kind of the most important thing here. I drank so much coffee that I'm scribbling messy. Okay, we're going to get rid of the mercury. And what happens is that we're adding a hydrogen here. There is a hydrogen already, but we're getting rid of the mercury and adding another hydrogen. But we don't touch this group here. We still have our methyl and our OH group here. Now, this is not chiral anymore, right? We don't have a chiral center, okay? So we wouldn't even write racemic. This is just a non-chiral product. Now, the key here is that there is no control here with addition of the H, okay? And we won't go over this mechanism. You don't need to know this mechanism. It's quite involved, and I'm not even sure if everyone knows exactly what happens here, but it's a radical type mechanism. So in this case, we don't make a chiral center. Just know that the hydrogen, essentially, if it could have made a chiral center, it would have racemized there. Let's do an example of that together so that way we really have this down. We're going to take actually the same intermediate, and I'm going to show you what happens to that chiral center if we do end up making one. It'll make sense in just a minute. Let's redraw our intermediate here with the mercury. Okay, and instead of sodium borohydride, we're going to be using sodium borodeuteride. Now, this deuterium that we're going to be adding is going to form a chiral center. So we're going to have this chiral molecule. So we're going to see what happens. Now, I said that there's no control with addition. And let me just focus here again. This is deuterium, which is simply a heavy hydrogen. Okay, so we've seen this before with our chiral centers, but it's just a heavy H. And it's going to actually give us a chiral center, which is kind of neat. So when we do this, we have no control with addition of this chiral center or addition of this deuterium. So we're actually going to get two products. So we're going to get the deuterium adding on the same side. Plus, we're going to get the same product where the deuterium has been added on the other side. These two are diastereomers. Now, we do have a racemic of both. We actually get 4 products here. Oh, and I should note that, like we had on the previous slide, these are racemic. These 2 products here are diastereomers. So let's kind of go over what just happened here. We make 4 products, so there's 4 total. The key here is that we had a racemic product in the beginning, and we knew that both of the centers here could be switched, okay? And so we started out with 2 products, okay? So we had 2 products that we started out with. And then what happened here is that this center with the deuterium is now both R and S, okay? So for the product, we end up getting 2, so we have to start with 2 products, and each of those 2 products now has another product it could form, where the deuterium's above or below. It might be a useful exercise to draw all 4 of the products out on your paper to understand why we're drawing this, where it says racemic, but there's 4 total. And the 2 that we have drawn, these are diastereomers, but they each have an enantiomer. So 4 total products here. And that's it for our oxymercuration and demurcuration. And in this video, we talked about going from an alkene to an alcohol without any rearrangements like we see with acidic conditions. All right, I will see you in the next video. We learned oxymercuration. Give me a high five. High five. Thank you. Yeah.